Good morning. Happy Monday. Today's a great day. We're going to be talking about some exponent rules. Today is day 4 of our class together. To let you know about how this week will sort of work, we're going to be discussing exponent rules today, how they kind of fit together into other pieces. Tomorrow, we should be discussing, most likely we'll be discussing like polynomials. And then next week we decided to do the graphing portion, mainly because I wanted to get through kind of the algebra intensive ones first, because many of you that is your skill set, and I wanted you to have a good start. And if it isn't your skill set, it's one of the more important things in this class, and especially going into next year if you're taking college algebra. So make sure to note these kinds of problems, kind of how they fit together, and the different rules and properties we're going to be discussing. So let's look forward to that, and we'll see you guys on the other side. All right, for today, as I said, we're going to be discussing some exponent rules. Now, let's begin with a very, very complicated yet simple question. What on earth is an exponent? So, for today, before we can talk about exponent rules and kind of how they fit together, it's important to note we have to understand at its fundamental principle what an exponent is. So let me ask a very, very basic question that many of you guys could do without any assistance whatsoever. 2 squared. If I ask the question, what is 2 squared? There's actually multiple answers. Okay, so the first answer most people jump to is 4, right? Because that's the answer, right? That's 2 squared. That's simple. But there's also a secondary answer, because 2 squared is actually an operation. It stands for something. 2 squared is actually just the number 2 written that many times. Which means if I wanted to do something like 3 squared, you could just jump straight to the answer 9, but you could also think of it as the number 3 written 2 times. So in this case, the number down here at the bottom, referred to as the base, represents it here, and how many times it's represented is the power. And so if I want to do something like 17 to the 4th power, what that means is, if I don't have a calculator to just type that in, you can even use one of those old function calculators to get the answer. You just take 17 times 17 times 17 times 17 4 times. And so at its basic, that's how you define an exponent. And note, at any point in time, this is a valid step. You may either take a number and convert it into natural form by simplifying, or from exponent into multiplicative form, and backwards. So any of these is an option. This is the same as the middle, which is the same as the end in all of these cases. Now, where it gets trickier is remembering that this holds true when it comes to variables. If I say something like x cubed, like x cubed is just x cubed. There's no way to simplify it to like 4 or to simplify it to like 9 like we did up here. X cubed is just x cubed, but you may at any point in time write it as the number x written out 3 different times. And at any point in time, you may see 3 x's that are all being multiplied and write them as x cubed. This is a natural progression of exponents. So for the moment, I want to make sure to illustrate a basic property of exponents. First thing, I can define any number of exponents, such as 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. I can define any of these in terms of their number, referred to as the solution, or in terms of how many there are. And so at any point in time, you may convert back and forth between the expanded form of 2 times 2 and the more proper exponential form of 2 squared. And of course, you may take the appropriate step, if necessary, to simplify these. So 4, 2 times 2 times 2 would be 8, 2 times 2 times 2 times 2 would be 16, 2 times 2 times 2 times 2 times 2 would be 32. At any point in time, you may take any of these steps to go back and forth between them. But this exposes more rules, as you will soon find. The first rule I want to talk about, I like to refer to as the identity rule. What the identity rule states, wow, I can't spell rule, it's Good Monday. All right, rule. The identity rule states that If there is not an exponent, so if I have, for example, the number 6, you may write it as 6 to the first. Now, as it turns out, this is a pattern that explains why 6 is also 6 to the first. Because if you look in here, going up in power causes our number to multiply by 2. So going up in power from 2 squared to 2 to the cubed means I have to multiply by 2. So going up in 1, so when I add 1 to the power, I have to multiply my solution by 2 to get my next answer. So I take the 4 multiplied by 2 to get the 8. So to get from 2 squared to 2 cubed, I just take 4 times 2, which is 8. To get from 2 cubed to 2 to the 4th, I multiply by 2 again. To get from 2 to the 4th to 2 to the 5th, I would add 1 to the power. But what that means is I have to multiply by 2 when it comes to the solution. Now, here's the kick, where we start to see the rules develop. If I wanted to go the other way, like, I could hold this pattern and keep going, right? I could continue and be like, okay, this will help me to find 2 to the 6th, because 2 to the 6th would just be the number 2 6 times, and to get that answer, I would just take 32 times 2 and get 64. If I want to find 2 to the 7th, I could just keep this pattern going. I could keep adding 1 and multiplying by 2 and keep getting the next answer. But what happens if I wanted to go backwards? What if I wanted to go this way? Or this way? Well, if I want to go backwards, I'd have to do the opposite operation, meaning I'd have to subtract 1 from the power. My power of 5 becomes a power of 4. My power of 4 becomes a power of 3. My power of 3 becomes a power of 2. I have to subtract 1 from the power, but to move backwards, I'd have to divide by 1, or divide by 2, in order to get my solution to work. So I take my numbers, I would divide by 2. So this tells me that if I wanted to go backwards from 2 to the 5th to 2 to the 4th, I would subtract 1 from the power, meaning the 5 becomes a 4, and I would divide the solution by 2. So 32 divided by 2 would become 16. Divide by 2 again would become 8, which is why 2 to the 4th becomes 2 to the 3rd. And then divide by 2 again, 2 to the 3rd becomes 2 to the 2nd, which means 8 becomes 4. But if I do that, that means that if I wanted to continue that pattern, I'd end up with 2 to the 1st power. So I would subtract 1 from the power, which means in order to get that solution, I would have to divide my answer by 2. Which means my 4 becomes a 2. Meaning 2 and 2 to the 1st are the exact same thing. Same as 2 squared is the same as 4. Same as 2 cubed is the same as 8. Which means the number 2 without a power is equivalent to the number 2 with a power of 1. And notice the middle pattern also makes sense, right? This is the number 2 written twice. This is the number 2 written 3 times. This is the number 2 written 4 times. This is the number 2 written 5 times. This is the number 2 written 1 time. However, this leads us to our next rule. What if I kept going? This is referred to as the 0 rule, or the 0 power rule. What it states is that if you have a power of 0, the answer is 1. And this works for variables as well. So if I have something like x to the 0 power, it is also 1. So let's investigate our property. If I wanted to continue this pattern, so I'm going backwards still. Oops, this one. Here I would be multiplying by 2. If I wanted to continue backwards, I'd have to divide by 2 again, which means I'd have to subtract 1 from the power. Now watch what happens. Well, if I subtract 1 from the power, this becomes 2 to the 0 power. If I divide by 2, 2 divided by 2 is actually 1. And so this is where the middle one kind of breaks down. Because how do I write the number 2 0 times? I can't really do that. But the top and bottom ones still work. This middle one is only to help us interpret the top becoming the bottom one. And note that this pattern holds true with any number and with any variable. That's why a 0 power is always 1. And so if you look here, the 2 dividing by 2 to move backwards would be becoming 1. Subtracting 1 from the power would make this 2 to the 0. It holds true. And if I wanted to go back forwards, it would still hold true. Right? To move forwards, I have to multiply by 2, 1 times 2 is 2. Just like 2 times 2 is 4, and 4 times 2 is 8. The pattern continues to hold. In this top part, it still holds as well. I'm always following this pattern written in blue and this pattern written in orange. So, if I wish to add 1 to the power, I have to multiply by the number. If I wish to subtract 1 from the power, I have to divide by the number. So if I want to go from 0 to 1, I have to add 1 to the power, which means I have to multiply by that number. So from 0 to 1, the 1 becomes a 2. To become 2 to 3, I have to take the power of 2, add 1 to the power to become a 3, which means I have to multiply the solution by 2 to become 8. And, as you might imagine, if we did this one more step, something interesting happens. So, once again, I have to add 1 to the power, multiply by 2 if I'm going to move to the right. But if I want to move to the left, I'd have to subtract 1 from the power and divide by 2 to the left. So watch what happens. Here to the left, I would get 2 to the negative first power, because 0 subtracting 1 would become negative 1. But watch what happens here. I'd have to divide by 2. Now 1 divided by 2 is 0.5, but I prefer to write it this way, as 1/2. And you notice that this power of 1/2 is just this positive power on the bottom of a fraction. And so there's a funky way to write this. If I write 6 to the negative first power, this is equivalent to 1/6. Notice the negative power does not mean the answer is negative. It implies where the 6 is, just like it did up here, right? A power of 2 tells me there's 2 times. A power of 3 tells me there's 2 3 times. A power of 4 tells me there's 2 4 times. A negative power tells me there's that many just on the bottom. So 6 to the negative first power is equal to 1/6. X to the negative first power is equal to 1/x to the first. And this holds true for any negative power. So for example, if I have like 4 to the negative third power, we'd say it's 1 over the number 4 3 times. If I have here x, let's say y to the negative second power is equivalent to 1 over y's. Notice that the number of y's doesn't change. What changes is where they are. This tells me, hey, there are negative 2 y's. What does that mean? There are 2 y's that happen to be in the bottom. And here's how we write these rules in general. The identity rule. We're going to use the letter A for each of these, where we have A to the first power is the same as A. This is the identity rule. The 0 rule says A to the 0 power is always 1, where in this case A is any value. It can be a variable, it can be a number, it can be a combination of things. But if it has a 0 power, the answer is 1. It simplifies to 1 every time. And then finally this last one, A to the negative B power is equal to 1 over A to the B power. Notice what doesn't change. It still has A, it still has B. What changes is where it's at. The negative power means that I still have BA's, it's just they happen to all be in the denominator as opposed to being in the numerator. These are our first 3 rules, and these are good rules to have for tonight's homework assignment. But there are actually a couple more, so let's go through them. Let's go see, we have a product rule, a quotient rule, we also have a power rule, and there is even a distributive rule. Now let's talk about each of these in turn. Before I do that, I need to make a special note here, and this one's the big one, the big star for the day. All of these rules apply only when powered or multiplied. If you see an example that has a plus sign in between two terms, you cannot apply these rules. We'll look at what that looks like in a little bit, but for now, that's kind of where I'm going to leave it. If you see addition or subtraction in any of your homework, which you won't, but in the future, if you see addition or subtraction, these rules do not apply at this time. These rules can only apply if you have a power to be considered or something being multiplied to be considered. Let's look at each one. The product rule. The product rule states if I have two functions, a to the m times a to the n, notice I have exponents and powers being multiplied or powered. So I have an exponent times another exponent. What this means is they will be added together. The quotient rule, if I have the same setup, a to the m over a to the n, what it means is they will be subtracted. If I have something like a power, so if I have a to the m to the n, there's two versions of this, so I'll showcase the first one, but I'll box the second one. The order isn't important, so you could also write it as a to the n to the m, but the better one is to just multiply the two solutions. This is the one that's bigger. And then finally, the distributive property. There's two versions of it. The first one is distributing with a product. The second one is distributing with a quotient. So if I have a product like a times b to the m power, it becomes a to the m times b to the m. Notice the power goes to a and the power goes to b. Notice what's in between them? Multiplication. Rules only apply if there's multiplication. If there had been an addition sign between these two, we could not do this rule. The quotient is the same way. If I have a over b to the m power, this is a to the m over b to the m. Our goal today, the big goal when you see a problem involving these kinds of problems, is to simplify. Now, when we say simplify, there's something very specific we're looking for. We want all exponents positive. What that means is there are no zeros exponents allowed. Remember, a zero isn't positive, it's just zero. And there can be no negative exponents allowed. If you see a negative exponent, you have to fix it. If you see a zero exponent, you have to fix it. And all distribution done. So when we say the word simplify for the problems today, what it means is these three pieces. There can be no zero exponents, there can be no negative exponents, and everything has to be distributed. If any one of these fails, you are not finished. There must be a property or rule that you can use between one of these seven. Now, at any point in time, any one of these seven can be at play. So let's take a look at some practice problems. I'm going to keep this sheet handy. It's really nice to have as I pull up my practice problems. We're going to do a couple of these. In fact, we're going to do 6. Okay? Let's take a look. So, before I do that, let's talk about those properties one more time and kind of showcase an example of each. So let me showcase the product property. Here's my example. If I have, and this is ones you can check with a calculator, that's why I'm doing them. If I have 6 squared times 6 to the 4th. So notice that for this property to hold, the base, the bottom number, has to be the same. So a and a, 6 and 6. That's acceptable. So what's this mean? Well, I take the two powers, which are 2 and 4, and what I'm going to do is I'm going to write a new statement. So this is my solution. It's going to have the same base, so these are both 6's, so this will have a base of 6. But the power is going to be the two other bases being added together. So 6 to the 2 plus 4, or 6 to the 6th. Feeling some devil worship going on here. So 6 squared times 6 to the 4th becomes 6 to the 6th. Notice that the bases have to be consistent in order for this to work. If the bases are inconsistent, like say 2 squared times 3 squared times 2 to the third. If the bases are inconsistent, you may only do this rule with ones that have the same base. So I could take these 2, make this become 2, 2 plus 3, and then the 3 just stays on its own. It doesn't do anything, because that 3 one doesn't have any partners to dance with. And so in this example, this would become 2 to the 5th times 3 squared. And if you type this statement into a calculator, this left-hand side is equivalent to this right-hand side. So you know it works. So this is the product rule. The quotient rule runs pretty much the same. Here's my example. If I have something like, so again, I want to use calculator version. So if I have 5 to the 4th power over 5 squared. Now, first of all, I'm going to do it once using the rules, and I'm going to do it again, kind of showcasing how we know the rules work using a different property. So if I do the rules, notice that these have the same base, 5 and 5, which is required by the rule. We take the 2 powers, we keep the same base of 5, and then we take the 2 numbers, the top number minus the bottom number. And so in this example, 5 to the 4 minus 2. 4 minus 2 is in its own separate parentheses, so we have to evaluate that first. 4 minus 2 would be 2, so this becomes 5 squared. Now, how do we know that's right? Like, if you believe the rules, great, but if you don't believe the rules, let me showcase how to do it a different way. So this time I do the exact same problem, but now I'm going to use that rewrite property, where I can take a power and rewrite it as multiple different pieces. So let's take a look. 5 to the 4th would be 5 times 5 times 5 times 5. It'd be the number 5 written 4 times. On bottom, it'd be the number 5 written 2 times. Now, how do we know this works? Well, remember there's a property of algebra which states if there's something on both top and bottom, you may cancel it. And look what's left behind. We have 5 times 5. And 5 times 5, if we use that property another time, 5 times 5 just means we have 5 squared. Your goal tonight should be that no problems do you need a calculator. Because for many of the problems we have, a calculator isn't all that helpful. Because if I do the same process with a variable, I do it the exact same way, right? If I have x to the 4th over x squared, well then I do the exact same thing. I would just take x to the 4 minus 2, which becomes x to the 2nd power. Now, if for some reason you end up in a situation where one of these rules is broken, you have to continue until it's not broken, using different properties. So let me showcase another quotient before we continue. Let's see. I'm going to do 7 to the 3rd power divided by 7 to the 8th power. Now, again, I'm going to do it 2 ways. One way to showcase how the rules work, and one way to show a way to work around the rules. So 7 to the 3rd over 7 to the 8th, according to my property, I would keep the same base because they have the same base the entire time. So 7, 7, 7. And what I do is I take the top power, which is a 3, minus the bottom power, which is an 8. Now, 3 minus 8 will become 7 to the negative 5th power. Now I want you to notice this is not acceptable. According to my rules, I can have no negative exponents allowed, which means 7 to the negative 5th is not allowed. Thankfully, there is another rule. Negative powers flip to the bottom of a fraction. So this means I still have 7 to the 5th. What happens is where it's located. 7 to the 5th goes from the top of a fraction to the bottom of a fraction. These two are equivalent using this rule. So 7 to the negative 5 power equals 1 over 7 to the 5th power. So negative powers go to the bottom of a fraction. So you are not finished until it meets this form. Now let me showcase this one more time using that other way, just like we did before. So this would be the number 7 written 3 times divided by the number 7 written 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Now, if you'll notice, we use those same properties we did before. 1, 2, 3 cancel. Here's the issue. The reason why this one's kind of rough is if you don't remember what happens. Because I factored and deleted everything on the top, which means there should be a 1 left behind. Remember, when you cancel like this, there's always a hidden 1, because 1 times anything doesn't change anything. So there's always a hidden 1 there. Same on the bottom, it's just not important. And on bottom, we end up having the number 7 left over. How many times? 5 times. And so no matter what, I should get the same solution. It's just this one avoids the problem of forgetting this. And so this is your quotient rule. The power and distribution rules are all pretty similar, so I'm going to jump straight to some examples that are much like your homework problems. So, let's take a look. We got a total of 6. I'm going to start with A. A states we have 2uv. Now v has a negative power on it, and then a negative power on the outside. Okay, so our first example, our first real example that's like your homework. Okay, so how do we solve this? Well, if you use a property, you're on the right track. So I have all of these different properties I can use, right? I can use the identity rule at any point in time. I can use the zero rule. I can use the negative rule. I can use the product, the quotient, the power, and the distributive rules. Like, all these rules are acceptable at any point in time. The goal is just to figure out, which way to go first. So in this case, I'm actually going to take my first step. I'm going to rewrite this, because I'm going to use the identity rule. This becomes 2 to the first power, u to the first power. V already has a power, so I'm going to leave it as v to the negative second, and then a negative third power. Now, what am I going to do next? Next step, I'm going to use my distributive property. With a product. Now, the distributive property of a product states that this power on the outside gets multiplied to each piece of the inside. Now, here's the trick. If it already has a power, right, then I have to use the power rule. If it already has a power, then I have to use the power rule to get it fixed. The distributive property distributes to each term. I take m times the a's power and m times the b's power. And so if there's any powers already there, I have to do that step. Let's take a look what happens. This becomes 2 to the 1 times negative 3. U to the 1 times negative 3, and V to the negative 2 times negative 3. Now, let's simplify using some math. Many of you guys will skip this middle step. This becomes 2 to the negative third power, U to the negative third power, V to the sixth power. Now you might notice, this is not acceptable. I have negative powers, and according to my simplifying rules, no negative exponents allowed. So, I'm not finished. I'm now going to use the negative power rule, this one, to fix the two that have negative powers. Notice I only fix the two that have negative powers. I do not fix everything, because they're the only pieces that are wrong. I'm going to fix this piece and this piece. So v to the sixth is still v to the sixth. Now, 2 to the negative third power becomes 1 over 2 to the third power. U to the negative third power becomes 1 over u to the third power. And v to the sixth just stays v to the sixth. Last step. You can simplify this, because I can take top times top times top. Give me v to the sixth. And on bottom, I would have 2 to the third u to the third. This is a good answer. Now you can take 2 to the third and write it as an 8, making this go from v to the sixth over 8u cubed. That's an optional step. I do not consider it a requirement, because I'm more concerned that you use the rules correctly. Because these two are equivalent statements. This statement and the end statement are the same. It's just they've applied properties along the way to get them to match. It's going to be work through B a little faster. E squared, e to the negative third, sorry, f to the negative third power, over f to the negative first power squared. Now, I apologize. This should be f. Okay. F to the negative third power. All right. Now, I can choose to simplify inside first using the quotient rule. All right, I could simplify that inner piece because I have f to the negative third on top and f to the negative first on bottom. Or I could use the distributive property first, using the quotient rule of the distributive property. Which one I do doesn't matter. It will give me the same result as long as I follow my rules. So I'm going to distribute first. So this becomes e to the second times 2, f to the negative 3 times 2, over f to the negative 1 times 2. That 2 power is applied to each of the 3 pieces. I can simplify this. E to the 2 times 2 would become e to the 4th. F to the negative 3 times 2 would become f to the negative 6th. F to the negative 1 times 2 would become f to the negative 2. Now I can use that property of division, the quotient property. This becomes e to the 4th. Notice the e has nothing to divide, so it stays the same. This becomes f to the negative 6 minus negative 2. Notice we need to put the double negative here, and that's okay. Double negative will just become positive, which ends up meaning that I end up with, down here, e to the 4th, f to the negative 4th power. Okay. Now, I come across the point where I no longer am allowed to have negative exponents, so I take my next step. My next step is negative exponents are fixed. This becomes e to the 4th times 1 over f to the 4th. And then we can combine, becoming e to the 4th over f to the 4th. None of my exponents are 0, none of my exponents are negative. This is an answer. And notice how we just apply the rules a bunch of different times. In a given problem, you may end up using the same rule multiple times, or you may end up using a bunch of different rules. It kind of depends. So this will be your homework tonight, is to use and apply these rules to get to a solution. Now, because it's going to be dealing with a lot of variables, there's not a lot of ways for a calculator to help you. Keep that in mind. Don't become distracted by trying to plug this into your calculator and get it to do it for you. It doesn't always work. Although things like photomath do work on this, so use that to help check your answers, please. Otherwise, that's it for today. I hope you guys have a happy Monday, and I will see you guys tomorrow.